Okay, so I think we're going to start. People are still joining, but we have to be on point the time we promised. So we're going to start, and whoever is joining later, everything will be recorded. So you'll be able to watch the beginning if you miss something, or if you need to continue watch it later, don't worry about it. So welcome, everyone. Thank you for joining Newsight webinar. My name is Michal. I'm Director of Strategic Partnerships at Newsight Imaging. And this is Uri Baror, Senior Director of Engineering at Newsight.
Thank you, Michal.
So today we're here to talk about our exciting NSI1000 sensor, about our technology, our cool features, enhanced time of flight. You're going to see here cool demos today. So please stick with us. It's worth it. First of all, I'm going to present a little bit of the agenda, what we're going to have in this webinar today. I'm going to present the schedule, do a little bit of a company introduction. For whoever haven't heard about Newsight before or our products, it will be a good review. Later, I'm going to talk 5 minutes about possible market opportunities, applications you can use the chip to, but again, it's going to be short. There are multiple applications. We're going to touch the main ones. Later, I'm going to give the stage to Uri, which will discuss the NSI1000 chip, the enhanced time of flight technology. You're going to see some short demos. And eventually, we're going to go to the features of the NSI1000, and you're going to see a demo of 8 features, again, with the introduction of the kit itself. So please bear with us. It's going to be a little bit long video, but it's worth it. And eventually, we're going to leave it to Q&A, a short Q&A for you to have an open discussion, and Uri and myself, all the questions you have. So let's start. So Newsight Imaging is a semiconductor company. We are manufacturing 3D CMOS image sensor chips for 2 main applications. One is machine vision, and the other one is spectral analysis. Some of you probably heard about our recent cool development virus detection in COVID-19. We had the recent headlines about. We're going to discuss the machine vision applications, which are exciting as well, and we have a lot of updates on that. So this webinar will focus on the machine vision, but again, if any of you have also questions about the spectral, later on you're going to have our contact information. You can reach out to us. We'll be happy to answer your questions as well. So although the company was founded in 2016, we have quite a traction. We released 4 sensors to the market. Some of them are already integrated into existing products in the market. We're collaborating with top research organizations like Fraunhofer. We are supported by the Israel Innovation Authority. We receive grants. You see some cool vendor here. So basically, although we're a startup, we have quite a traction, collaborating with top organizations and that are validating our technology and working hard to present it to the market. So regarding market applications, what you see here, we chose the main ones that we thought might be interesting. But again, every time we get a new requirement of a new application, so we're here for you to support. If you have any kind of inquiry for a specific application which is not here, of course, the NSI1000 is very flexible. We'll be able, you're going to see it soon when Uri will present the chip, but you'll be able to modify it and use it for many machine vision applications. The one we chose here is the ones we saw that have a lot of inquiries recently and very trendy in the market. Everything regarding robotics vision, if we're talking about vacuum cleaners, AGV, lighters, etc. We see that the NSI1000 has a huge advantage giving, for example, stairs. If we talk about vacuum cleaners and you need the field of view of anything be more accurate, if you needed to also be able to identify stairs or any other obstacles, we see that we have a huge advantage there and a huge success. We get it from customers. If we talk about Industry 4, everything regarding to quality inspection, automatic sorting machines, the NSI1000 frame rate, and it can detect even small irregularities very fine. So we see there's a lot of advantage in those markets, and we get a lot of positive feedback from customers. And automotive, everything regarding to ADAS, the multi-triangulation feature you're gonna see shortly, presented by Uri, you'll see that it has a huge advantage for ADAS applications like blind spot, mirror monitoring, or real-time tire monitoring, etc. To have something which is low cost, very accurate, effectively giving you a depth points. These are the main applications with you here today. But again, feel free to contact us if you have any kind of application in mind. We have all our team and application engineers here to support you and to show you our advantage for your exact inquiry. So let's go to the point. The NSI1000, I'm going to leave this to Uri to share a more technical overview about the chip and explain to you its advantages.
Thank you, Michal. Okay, so the NSI1000 is actually the fourth product from Newsight. Unlike the first product, which were line sensors used primarily for triangulation, the NSI1000 is already an array. And being an array, it has a global shutter with 60 transistors. It's manufactured at Tower in Israel with a 0.18 micron CMOS. Now you can see the block diagram of the chip. You can see the main part of the array itself with 32 lines of 1024 pixels. And we also have two more lines which are used for triangulation and actually backward compatibility with our previous products, which can reach 2048 pixels. So they are basically for high accuracy and high resolution. Now we have all the digital block inside, so we have full control over the array, the analog part, and actually every aspect of the chip can be controlled by the digital block. It's very flexible, and we also have 32 configurations that we can load into the chip, meaning that for each frame, we can do something else. Each frame can have its own configuration, and the chip automatically moves between one to the other in a round-robin manner or also in some other ways. We have all the analog circuitry inside the chip too. So we are using column parallel architecture with the A to D per column. And we have CDS inside, and we can also program the gain and the offset of the analog part, which means that also the analog part is fully programmable and flexible. We can support any number of lines, so the user can select how many lines he wants to use from the array. And another cool feature that we have in the chip, we'll also see it in the demonstration, we do internally the peak detection, which peak detection calculation with the center of mass algorithm. And this is very helpful for multi-triangulation where you have to do many calculations for 32 lines. So this is done internally. Now let's talk a little bit about the eTOF technology, which is one of the main features of the chip. As you will know, there are several technologies for measuring distance using the light. So the basic one is the time of flight, in which you actually measure the time itself that takes the light to go to the target and back. This is not useful or actually beneficial if you want to go to low-cost CMOS technology, since you need to have very high frequency, very high clock frequency. So there are several methods in the market to do it indirectly, like phase shifting or a structural light. We selected to base our product on the eTOF, which you can see on the right-hand side of the screen, in which we send a pulse of light, and at the same time, we open two windows for measurement. One of them together with the sent signal, and the other one actually starts measuring as the signal turns off. And as you can see on the second line, you can see the return signal, and the return signal falls between the two windows. So if the object is very close, more energy will be collected in the first window compared to the second one. And when the object is moving far from the sensor, you have more energy, more relative energy, I would say, collected in the second window compared to the first one. Of course, the total energy will be lower as the distance increase, but the relative energy in window 2 will be larger and larger compared to the first one as the distance increase. Now, we took this eTOF technology and actually have now our trademark eTOF technology based on it, in which we added several cool features that, and some of them are patent pending, which actually takes this process one step further. So the first thing that we did, we actually divided the array into groups of 4 pixels. You can see on the right-hand side, we call them X, Y, W, and Z. And as I said before, we have a very flexible digital block in which we can configure each of these pixels to have different timing and different exposure time. So basically what we do, we can have 4 measurements done at the same frame and at the same time. So one frame, we can take all the windows that we saw before, the A and the B, and the ambient light, which is used in order to get a better accuracy. We can also do one window, which is A plus B. This cannot be done, by the way, with pixels which are multi-tap because it's pixel. So we can also do this and measure A plus B in one window. Doing this will give us a better accuracy since there is no cut between the A and the B, the measurement of A and B. Now this structure actually copied all over the array. So it's copied to the right and to the bottom and covers the whole array with the 4 pixel. Now we are actually using our multi-set enhancement in which we can cover short and long distances frame by frame. So we can do one frame for long distance and one frame for short distance because we don't know what the distance is. So we can send out different configurations and cover the whole very high dynamic range. And of course, we also have some redundancy, as you see, because we have the A measurement, the B measurement, the A plus B. So the software outside can calculate the distance in various ways and choose the best way to measure it. So sometimes it will use the A, sometimes the B, can do average between them. And finally, what we can do demo sizing because we can actually have one set with X, Y, W, and Z. And then in another set, we can mix the pixels and have Y do the X and Z do the Y and vice versa. And this way, we can actually retrieve the full depth resolution of the whole array. Okay, now we'll go and we'll show you a demonstration of this eTOF technology.
Yeah, just a second.
We put the system in front of a wall about 4 meter distance, and we start the application and loading the configuration files. Then we press start, and the system starts continuously to make a distance measurement. Now you can see right that after the parameters loading, it shows the 4 meter distance. And when I insert the target, it right away drops to 1 meter distance. Okay, now we see the live distance measurement is being carried out. Once we move the target from about 2 meters up to 4 meters in live.
Okay, we see we have some questions. Again, we're gonna collect all the questions you're asking during the session, and later in the Q&A session, we're gonna answer those questions, so don't worry. Just a second.
Okay, we've just seen in the movie that we covered about 4 meters of the distance, actually managed to reach 85 meters outside. So this is just a short demonstration of the short distances. Now let's go to see some other features of the NSI1000. As I said, the main feature is the eTOF, and we didn't mention one feature that we have in the chip, the ability to accumulate the light in the pixels. So we can collect thousands, many thousands of short pulses in the pixel itself. It is done in the pixel before the readout and before the A to D conversion. So basically, it's the raw signal that comes into the pixel. And this gives us a very high accuracy because we can work with short pulses, but also it covers the long distance because we can collect the small amount of light that comes back from a far and get good energy to make the calculation. A very high frame rate. As you can see, when we work at 100 megahertz, we can reach 100,000 frames per second of 1024. If we go to the whole array, the full array, we can reach 3,000 frames per second, which is also very high frame rate. We can use, as I said, we have multi-set in the chip, so we can use it as a camera. We can multi-triangulation of up to 32 lines. We can, of course, do the eTOF. And we can combine all together because, as you can see, we have 32 configurations. So we can do in one frame, we can do eTOF, and in the second frame, we can take a picture or a camera and then fuse them together to get a full depth image. So depending on the application, you can program the chip to do anything that you need. Now, another cool thing that we have is the auto exposure mechanism inside the chip. The chip can detect if it has low light coming in, and then it will jump to a set with the higher exposure time. Then, of course, if there is too much light, it will go to a set with a lower exposure time. And as I mentioned before, we have on the fly, actually, peak detection mechanism calculation. So while sending the data out, we already calculate the peak by using the center of mass algorithm. And to add, to actually help this peak detection mechanism to work better, we also have a moving average algorithm also implemented inside and done on the fly on the data itself. Now we will see a movie video that shows all these features of the chip.
Just another thing I wanted to add, that the eTOF demonstration, you see it's 1 point, and we're going to soon release the multi-point, right?
Yes, yes. We're in the final stages of releasing the multi-point capability of the chip.
Yeah, so it's just a teaser, let's say. So we're going to start the video of the feature that you just heard by Uri. Important to say, what you're going to see first is the demonstration of the kit. Later on is going to be short demonstrations of each features. You have 8 features. So we try to extract it to be short as possible, minute to each feature, so it's not going to be too long. Of course, there's many things you can do with each feature, but it was important for us to show you the main point, and later on you can test and do yourself anything and explore the fullest the chip. So bear with us, and later on we're going to open the Q&A session and answer all your questions. Welcome to Newsight's NSI1000 features demo. We have here on the table evaluation kits of the NSI1000. The first one I'm going to show you is NSI1000 EVBA, which is FPGA based. With the board, you also have the cables included in the kit. On the board, we have already connected the lens holder and the lens on top of the sensor. This is also included with the kit. It's very easy and straightforward to connect to the board and perform evaluation. Of course, everything you see here together with the cables is all included in the kit, and it's available for purchasing at any time. The second one is the NSI1000 EBB, which is, here the sensor is exposed, but of course, as at the other kit I showed you just recently here in the FPGA, you will get the and the lens itself included in the kit as well. Here is also very straightforward to connect to the board, and you have the cables included as well to perform your evaluation. It's important for us to provide you all the tools to have a successful evaluation of our product.
Together with the kit, you have, of course, a demo tool, which will provide you to do a very straightforward and easy evaluation. We provide you documentation, including user manual, application notes, enable to use the fullest of the features that our product can offer. Shortly, we're going to show you a demonstration of the main NSI1000 features and how you can use them for your own target applications.
I'm going to show you the camera mode. For the camera mode, I will use the NSI1000 array. It is perfect for the Industry 4.0 and sorting application. I'm scanning Marilyn Monroe picture. Take a look at the screen. You can see the image bar below the energy bar. You can see the image bar, the picture itself being scanned. Take a look at the difference between the gray areas. You can see it clearly. That way you get a very high quality picture of what is being scanned. The digital binning enables you to use the full array as one line. You can easily detect the light that hits only some of the lines. As you can see on the wall, there is a black target with spots on it. Let's look at the energy bar. You can see a white triangle. Let's try and see it also in the energy bar, between the lines. Here it is. You can easily see it in the energy bar. Let's look. Let's find where is the higher energy of that triangle. Which line has the higher energy? Here it is. Now it's decreasing. And here it is. You cannot see it anymore. It's about line 23. It's the end of the triangle. Okay, now let's see it in the bin 60. It can easily detect the white spot, even though it doesn't cover all the lines. And here it is, binning 32. The NSI1000 array can provide triangulation of depth points. It can be used for industrial and automotive. As a target pattern, I'm moving it in the laser line on the board. You can easily see it in the image bar and also in the triangulation bar. You can very accurate calculate the heights of the parts of the object. Triangulation is known method of measuring distances. The returning light from the object hits the sensor. We can determine the location of the light and assess the distance. I will show you the classic triangulation. We will use the 4-bin triangulation. There's also an option to use 2-bin triangulation with 2048 pixels. There is another line with the new pixel line with also 2048 pixels. Okay, let's start and show you the triangulation. You can see the energy bar above and the image bar below. With a good signal, now currently the target. As you can see, the target moves and also the bar move along the pixel, the sensor. In order to increase the accuracy of the triangulation and multi-triangulation, the NSI1000 uses peak detection algorithm. With the center of mass algorithm, we can calculate the peak of the curve in the energy bar to a sub-pixel accuracy. The laser line is on the wall, and I'm moving now the target of the sensor. You can see the center of mass, the red line that marks the center, the peak of the line. There is a number below which indicates the position of the peak in the sensor. Now let's move between the lines and see the different peaks in the location. The auto exposure is the multisets. It prevents pixels overflow and pixel saturation in the NSI1000. It uses define upper and lower thresholds values. Also predefined sets with different exposures. Once the thresholds are exceeded, the auto exposure directs the sensor for the next frame. We'll explain the setup first. You can see the light source on a rotating stand. This is in order to increase the light on the sensor. Let's start. Okay, I will start the light source in order to increase the energy on the sensor. As you can see, the energy is increased, and once it drops immediately, basically we move to another set. Here it is. It is being and then decrease. And this is the last set because it is overflow. In cases where short length pulses need to be used, the pixel accumulation allows to accumulate enough energy in order for the return signal to be detected. It helps to increase the sensor's dynamic range by using a different number of for different distance measurements. Let's first look at the laser that's being transmitted. We have two configuration files that we're going to use, one with 200 pulses and the other with 2000 pulses. Let's first load the 200 pulses. Let's try to see it on the scope. Okay, here it is. You can see the pulses. Let's zoom out a little bit just to see the entire length of it. Let's also zoom in to see the pulses themselves. Let's zoom in a little bit more. The scale is 200 nanosecond here. Okay. I'll wait for the other config file. Now 2000 pulses. Okay, here it is. Same pulse length. Let's zoom out to see the entire size of it. This is 2000 pulses. Will it be different from the 200 as we seen before? Okay, now let's go back to the pulses and move away the scope. Okay. Now you can see the little bump that just appeared in the energy bar is basically the detected pulses of laser. The sensor detects it from the target. And this is what we get. Let's go to 1,000 pulses, 2,000 accumulation. Let's see how it looks like. As you see, much more energy. That is because we have more pulses to accumulate. The NSI1000 has the ability to run up to 32 predefined sets. Each set can perform different tasks, either multi-triangulation or standardization or camera mode and eTOF. Also, each set can have different exposure time. We are using 4 different configurations in order to detect the light spot on the wall. Please look at the 4 image bar below. The first one is the array, and the one beneath is the 2-beam classic line. The third one is the new triangulation, and is the 4-beam classic line.
The NSI1000 evaluation kits are available for purchasing. You can find it in our shop or approach us through our sales managers. If you have any questions, feel free to contact us.
So thank you for staying with us. Just a second, I'm gonna improve the mic so you can hear us better. Yeah, now we're good. So thank you for staying with us and seeing the demonstrations. We hope that it gave you a little bit of understanding of the capabilities of the chip. Again, this was a very short version of each feature. There are many things you can do with it, and we have all the documentation, as we told you before, application notes for the feature for you to be able to use it the best way possible. Of course, if you have any kind of application in mind that you think it might be useful, we are here for you with our support team, the application engineers, and of course the R&D managed by Uri is here to support everything you need. And please stay tuned to upcoming new demos like the multi-point and the other exciting chips that we have soon to be available in the market as well. So we're going to start the Q&A session. I'm going to start addressing for the questions I see here. So let's start. For some reason, yeah. So the first question is, which distance is the minimum for the short distance?
Okay, thank you for this question. What you saw in the demo, actually, I think we saw a minimum distance of about 50 centimeters. But of course, we can go lower than this. I can estimate about 10, 20 centimeters. It all depends on the system itself, how you place the laser light and where you place the sensor. I hope this answered the question.
Yeah.
Distances actually we can do. And for this, of course, the triangulation method is a much better one than the time of flight for such short distances. And I don't have the exact numbers now, but we do have the capability to do micron distances.
Yeah, I just want to add that we had some kind of
yes,
inquiry
in the past,
and we were able to do less than 4 microns, something like this. So
yes, it was around 4 microns,
yeah.
but
so again, we can, if you have a specific requirement, we can check it, and we can send you the specific specs that we can do. Next question, why should I use the NSI1000 rather than a laser to measure distance?
Okay, I hope I understand the question. If you are talking about the laser, like a laser measurement thing, this doesn't measure, doesn't take a picture of an array. We can do a full array of cloud cloud points, so we can have up to 32 by 1024 distances, not only distance that you measure with a laser point. If I understood the question.
The eTOF NSI1000 sensor is using a plastic lens or its optical path? That's the question.
Okay, this is a system issue because the NSI1000 doesn't have a lens. So the NSI1000 is a bare sensor. And once you build your system, you can put any lens on it. So basically, I think this is the answer.
Yeah, the one we provide with the kit is just a regular lens.
Yes, of course. But
yeah,
then, but then you can put any lens that you want.
Sure. Can we see the demo of eTOF result in real time?
The eTOF that you saw in the demo is in real time. So you saw that someone was moving the target and the distance was shown on the screen in real time.
Yeah, I just want to add that for the webinar, in order to make it for you.
To see the depth. Okay,
yeah.
Now there's another question.
Yeah,
to see the depth. To see the depth image, this is exactly what Michal said before, and we are now actually in the final stages of multi-point, and in multi-point you will see a depth image. You know, for one point you cannot see an image, but once we go to the multi-point, see the full image.
Yeah, and this will be available soon.
Very soon, so, yes.
Yeah,
we're in the latest stages of releasing it.
Yeah, so it's exciting as well. Next question. How is the eTOF calculation is done in real time? Is it done by host PC, or it can be done by embedded MPU?
MPU, yes. Okay. So basically, in the demo that you just we showed you, it was done in the host PC, but now we're actually retargeting the code into the MCU, and the board that's in the kit will include this this calculation inside the MCU. So it will be done in the embedded MPU.
I can see if we have some other. What is the maximal distance that NSI 1000 can support? What kind of weather will impact the accuracy in the application, like snowing, raining, fog, or windy?
Okay, the maximum distance, of course, it's a system issue. It depends on the laser power, optics. As I said before, we managed to reach 85 meters, but you know, very easily. We just took the system downstairs and tested it, and we reached 85 meters. But of course, you can do more than this. It all depends on the system. It's a system question. And regarding the weather and the ambient environment, we are actually now working on it and improving the way we measure. I know the big problem, of course, is snow and rain, but we are now actually working on improving the algorithms to cover these scenarios too.
Yeah, so I think we're gonna, we answered most of the questions. We have to ramp up, but please, if you have any questions, you can still contact us. You have the details here of myself and Shmuel, which is our corporate application engineer manager, who can support all your questions. And of course, he will involve the R&D and Uri for every requirement that you need. You can see here also contacts for North American inquiries. One of our distributors is here also to give support to the North American inquiries. So please feel free to follow us on social media.